Good morning, ladies and gentlemen. May I have your attention, please? Thank you. And so we're off and running now, the start of Unit 5, where we'll be dealing with modeling and applications, the first of which involves differential equations and slope fields. Today we're going to be finding the particular and general solutions to a differential equation. We'll be constructing the graph of the slope field that a differential equation produces, and we'll also be doing a little bit of matching to gear up for Friday's activity. All right, so firstly, can we find an antiderivative function y if dy dx, that is the derivative of y with respect to x, is given by e to the negative 2x? You bet your boots, we'll just find an antiderivative function, right, by performing an indefinite integration. So what did you get for number 1? What did you get for number 1? Courtney?
Negative 2x over 2.
Negative e to the negative 2x over 2. Awesome. Plus c. And why did you have the plus c, Courtney?
Because there could have been a constant that worked.
Absolutely. We could have had a plus 17/3 or a minus pi over 3, right, attached to this antiderivative function. And when differentiated, it still would have produced that result, dy dx equals e to the negative 2x. That's going to be key in our discussion today as we go to find the general solution to a differential equation. And you just did it, right? You just found a general solution to a differential equation. Awesome. Share your antiderivative function y for number 2, please, when I call on you. So then we go all the way back to like tangent. We haven't done tangent for a while. Kobe?
The opposite natural log.
Nice. Opposite of natural log of absolute value of cosine of x. Great. And again, we can include a plus c to account for the fact that, right, there could have been a constant added or subtracted on, and that would not have affected the value of the derivative of y. Now, you didn't have to include a plus c, right, because it just said find an antiderivative. If we said find the family of antiderivatives, then you need to include a plus c. Today we'll get in the habit of including a plus c if we find the general. All right, so now I wanted to include a little bit trickier one. The first two are like, warming up, gearing up for number 3. Who recognized the overall rule for number 3? You guys get the overall rule, Danny?
Inverse tangent.
Yeah, inverse tangent. And so upon initial inspection, I know inverse tangent where it includes 1 plus input squared on bottom. And this is not input squared, it's 1 plus x to the 4th, right? And yet, that numerator function, x, is to the 1st power. It's not a difference of 1 in degree between the denominator and numerator, which is typically the pattern for a natural log rule. So it can't be natural log. That's okay if we were to rewrite that denominator. If we were to rewrite that denominator as 1 plus input squared, what would my input be? Tyler? X squared. And what's the derivative of my input?
2x.
2x. And so if I had a 2x here, right, if I had a 2x here, then I know an antiderivative function for this. It would simply be the inverse tangent of, right, x squared, close input plus c. But I didn't have a 2x there, and so I'll have to account for that by including a 1/2. Now, I don't have an integral symbol here at all, right? But all I'm doing is I'm talking out what I would need if I were to find an indefinite integral. And so keep in mind that I don't have to have an integral symbol there to include a 2 times a 1/2. What's 2 times a 1/2? Just 1, so I have to change the value of that at all. In any case, my original antiderivative function y then will be of the family of the functions inverse tangent of x squared, close input, plus c times a 1/2. Sweet. So raise your hand if you got that. Anybody get all the way to number 3? Yeah? So tricky, Ricky, awesome, good job. What questions do you have on the Bellwork? All right, we'll pause and bless you. We'll go ahead and pause the recording and take care of our OTL check. Resume the recording. So ladies and gentlemen, you just saw 3 differential equations for our Bellwork today. Recall that a differential equation is simply an equation that contains 1 or more derivatives. In our Bellwork, dy dx equals e to the negative 2x is a differential equation because dy dx, that term, right, is the derivative. It's the derivative of that antiderivative function y that you ultimately found as part of the Bellwork question. The differential equation produces a graph that we call a slope field. And this slope field is a collection of those mini line segments that indicate the slopes that a solution curve would have if it passed through that general vicinity. And so, depending upon the location of a solution curve, when superimposed upon a slope field, right, it's going to have a different slope and direction, and we can show that, right, what the slopes of the solution curves would be by sketching mini line segments, right, that would represent like mini tangent lines, right, depending upon where you're looking. The general solution to a differential equation is exactly what you found for Bellwork. It's a family of antiderivative functions, and we can show that with that plus c, that constant of integration that we include in an indefinite interval. That's different than the particular solution. The particular solution, right, would be a single solution curve that satisfies some initial condition or given condition. Oftentimes that's called an initial value problem, but that all means the same thing. So a given condition, an initial value problem, those all mean the same thing. It means you know one point on the curve, so you're going to find the particular solution curve that satisfies the given conditions. That is the differential equation and contains the point of concern. Today we're going to practice making a slope field. We're going to practice finding the family of solution curves, that is the general solution. We're going to sketch a particular solution, and then we're going to find that particular solution algebraically. Time permitting, we're going to do a little bit of matching too to gear up for our Friday Community matching activity. Let's go ahead and take a look at a differential equation. dy dx, there's our derivative, equals x minus 2. The family of solution curves, y, right, must all have slopes that are given by the x-coordinate on the graph minus 2. Can we sketch a slope field for that differential equation? Well, absolutely. Depending upon the inputs, the independent variables in my differential equation, I can just make a table of values to get an idea of what my slopes are going to look like. So let's everybody go ahead and do that. Based on, looks like I only have x is the only variable in my differential equation, so I'll make an x dy dx chart. Based on the x-coordinate, this differential equation will return a different slope value, and then I'll sketch the mini line segment on my lattice and go ahead and get an indication of what the slope field looks like as a whole. So here we go. When I plug in 0 in for x, I get -2 for my slope. When I plug in 1 for x, I get -1 for my slope. When I plug in 2 for my slope, I get 0. I'm sorry, for x, I get 0 for my slope. When I plug in 3 for my x-coordinate, I get, what, 1? All right, let's go ahead and start sketching our tangent line segments, and we can add more or less. And so if x is 0, the x-coordinate is 0, that's everywhere along the y-axis. It appears as though my slope is a -2. How can I show that? I'll just show a little mini line segment that looks like -2 slope. When x equals 1, my slope is -1, right? If a solution curve were to come through any of the points where the x-coordinate is 1, the slope of that curve would be -1. So I'll show that with a little less steep line segment. When x is 2, then I have a slope value dy dx of 0. So what kind of line segments do I need when x equals 2? I need horizontal line segments. Good? And so on and so forth. 3 is paired with the slope value 1. It's easy to see after we start filling in our mini line segments that this slope field only depends on the x-coordinate. And you look at a particular x-coordinate, all of the slopes are the same value. So that's a good indication when you get your matching stuff on Friday, right? That if the slopes are all the same for a given x-coordinate, then the equation for the differential equation must only have x as the input. What happens as we continue going this way? We can get getting more and more negative. So steeper, right? Steeper. Right? How are we doing? Now, can we picture the family of solution curves? Yeah, depending upon what given information we have, right? We could sketch a particular solution curve that goes through a given point x comma y. Right now, I can generalize the family by considering, right, a solution curve would follow the signposts, would follow the direction of the line segments closest to it. And it looks like my family of solution curves would have what shape? Yeah, it almost looks like a parabola, doesn't it? It looks like a parabola. Cool. All right, let's go ahead and sketch the particular solution that contains the point -1, -1. So everybody, let's find that point. -1, -1 would be here. if I know a solution curve has the point -1, -1, can we follow these slopes around, right, and sketch its graph? Well, yeah, we'll follow the signposts. So something like that. Was this exact? No. You saw how long I took to do it. I just tried to follow the direction. When I passed through a given locale, I wanted to make sure that I was parallel with the nearest mini line segment, right? How did I do? Well, not so well. It might be a little bit lower. So it looks like this might be a little bit lower. All right. So we'll see. We'll see how we did. What do you mean we'll see how we did? Well, I'm going to go ahead and now find the particular solution algebraically that contains that point, and we'll compare with our rough sketch. So how do we do that? Well, we can only solve a differential equation if it's what we call separable, right, for our purposes in BC. In order to be separable, that means we can get all the x's on one side and all the y's on the other side through multiplication or division, all right? In this particular case, I only have x's on the right. If I multiply over that dx and consider it as a differential, quantity in itself, then I could get all the y's on the left, that is dy, is given by quantity x minus 2 dx. Are all my y's on one side, all my x's on the other side? Did I use any operation other than multiplication or division? No, so I'm good to go. And I can find the particular solution by integrating. To get from dy to my regular parent function y, I would need to evaluate an indefinite integral just like Bellwork. So I'll integrate both sides. On the left, I'll integrate 1 dy with respect to y. That produces y. On the right, I'll integrate x minus 2 with respect to x, and that produces x squared over 2 minus 2x plus c. Remember, we need to include our constant of integration to account for the fact we could have been anywhere along, right, that slope field, up or down. That constant would disappear when you differentiate. However, we do have a particular solution point. It contains -1, -1. So we can find that c by replacing my x coordinate and my y coordinate with, did I get everybody? With -1, -1? Cool. So let's go ahead and do that. So it looks like -1 is equal to -1 quantity squared over 2 minus 2 times -1. Did I get everybody? Awesome. So we can go ahead and solve for c algebraically. That means that -1 equals -1 squared is 1/2 plus 2 plus c. So c must equal 2.5 minus 1, -3.5, so -7/2. -7/2. Yeah? Awesome. So I found that c is -7/2. I'll go ahead and rewrite and then solve for y, but y is already solved for, so y equals x squared over 2 minus 2x minus 7/2. Awesome. All right, let's go ahead and make the graph of that and see how it compares with our particular. So we're going to compare that now with our sketch. So everybody, let's go ahead and grab our grapher. I'll bring my emulator over and we'll take a look. Bless you.
I figured you would.
So there I tried to make a lattice in my format there, and you guys can do the same thing by going to second zoom this format, and you can make the lattice points as well. I'm going to go ahead and enter our potential solution curve. What do we get? X squared over 2 minus 2x minus 7/2. And we're going to compare that with our sketch here. All right, so here we go.
Wait, one more time, how do you make a lattice?
Second zoom. And it looks like I'm off the charts. So I need to go at least -7.
Mine is perfect.
I even did blue. Perfect. So how do we do? Well, it's better than a poke in the eye, I guess. Yes. I'll take it, right? So it looks like algebraically we were to generate a solution curve, right, that is very close to what our informal sketch was. You guys see it? Yeah? A-okay? Did everybody find the format for the lattice? If you want to do lattice, you don't have to. Okay. Some of you, guys, some of you have the slope field program from last year in there. I know you do, right? I don't want you to use it today because I want you to do slope field analysis for your matching. But I'm going to upload those. For those of you who don't have it, I'm going to go ahead and do the I-link and upload that program for you, right, on Monday. We're going to be investigating Euler's method for the BC curriculum. All right. Enough talk. Now we eat. All right. So now let's consider a differential equation that doesn't depend on x, right? Now, for our second one, our differential equation depends on what variable? Y. And so for a given x coordinate, will I have all the same slopes vertically? No, I would anticipate for a given y coordinate, I have all the same slopes horizontally. Let's go ahead and find a table of values and make a slope field, you guys. This time, am I going to make an x dy dx chart? No, I'm going to make a y dy dx chart. How come? Well, because my slope field, right, my slope field, it depends on the y coordinate. So let's go ahead and get some values here. When my y coordinate is -1, the slope value return of solution curves is 0. When my y coordinate is 0, the slope value returned by my differential equation is 1. When my y coordinate is 1, the slope value returned is 2, and so on and so forth. So we can begin to get our little mini line segments and get an idea of what the solution curves look like. So horizontal tangents. When y equals -1, when y equals 0, we have a slope value of 1. When y equals 1, we have a slope value of 2, so a little steeper. I bet when y is 2, then slope fields are 3 values for slope. Yeah, so a little bit steeper still. And when y equals negative, when y equals -2, then -1 is our slope. Are you guys doing that? Wish I had picked that point. It looks to me like a family of solution curves, right, that adheres to the slope field. It depends what point we have on the graph. If we had 2, -1, I'd be stuck right here on this horizontal asymptote, and I never escape it. And so it looks to me like if I was on the point 2, -1, then I would forever be on this horizontal asymptote, and the solution curve would stay there. So what I'm going to do is I'm going to change it because I want to be a little more interesting and I want to see. So let's not do 2, -1, right? Let's change this to, how about 2, 0? 2, 0? Let's do 2, 0. Which means we want to do 2, 0. Everybody, we're good with that? Got that change? Cool. So 2, 0 is going to be our solution point, and we'll sketch the general that goes through that. So where are we? 1, 2, 0. So we're thinking that we'd come up like this, and then steeper, and then steeper, and then steeper. As our y coordinates get higher and higher and higher, our slopes are getting, right, steeper and steeper and steeper. What happens as our y coordinate gets lower? Well, it looks like we're going to level off as we approach, right, this horizontal line segment, and there's going to be nothing that's going to kick it over to get it down on the other side. So it looks to me like this is going to level off here. Getting closer and closer to y equals -1. Let's see if we're right. Yeah? Yeah? Let's do it. All right, so can we separate the variables? Uh-oh, I've got addition or subtraction. Right? Is this separable? It's still separable. I'll just treat this as a quantity. In fact, I'll divide both sides by quantity, y plus 1, and I'll multiply over the dx. And so absolutely, I can certainly divide over the y plus 1 as a quantity, right? Times 1 dx, so equals dx. And now integrate both sides with respect to y on the left and with respect to x on the right. This produces the family of antiderivative functions y given by what? Natural log of absolute value of quantity y plus 1 close bars equals, and the antiderivative of dx with respect to x is what? It's just x, right? X plus c. All right. Now is where we have a couple different paths we can go by, right? We could plug in our initial condition right now, 2, 0, in for x and y and solve for c, and then solve for y last to get our particular solution. That should be of the form y equals. Or we could solve for y now, leaving this general, right, c value, this constant of integration, leaving that in my manipulation, and then plug in at the very end. The choice is yours, okay? So you want to try doing it with a plug in right away like we did last time first and see how that goes? All right, let's plug in our initial condition right now before you have a chance to mess things up. Solve for c, and then solve for y last. Ready? Here we go. kidding, Marissa. So we're going to plug in our 2, 0 right now. That means that the natural log of 0 plus 1 is 1 equals x is 2 plus c. The natural log of absolute value of 1 is the natural log of 1, which is 0. 0 minus 2 means that c equals negative 2. Is that what you guys are getting? C equals negative 2? Yeah? Awesome. So we'll go ahead and rewrite natural log of absolute value of y plus 1 equals x minus 2. We can solve for y by undoing the natural log. What's the inverse of natural log? E to the, right? We can exponentiate. That is, rewrite x into the form base to the, in this case, e to the x minus 2 equals absolute value of y plus 1. That means that plus and minus e to the x minus 2 equals y plus 1, except we already used our initial condition. So I don't think we need the bars here because when x is 2, y equals 0, and that was positive, and so my input was positive, therefore I don't think I need the plus and minus. In either case, we can group this e to the negative 2, right? Isn't that the same as 1 over e squared? Right, 1 over e squared times e to the x. So I'm getting e to the negative 2 times e to the x equals y plus 1. That means that e to the x over e squared equals y plus 1. And that means y equals e to the x over e squared minus 1. How'd I do? I mess up 3 times? 2 times? Okay. All right. Let's go ahead and check. So here we go. We're going to go to our emulator, and we're going to put in e to the x regular plain Jane x over e to the negative 2, or e squared, so e and minus 1, chill on the backside. And we're going to pretend that our graph is going to make that picture, and we're hoping, and we're hoping, and we're achieving. Oh my gosh, that's pretty darn good. I want to change the window just so I can get a better screenshot. What do we want? Maybe negative 3.25. I'm going to try again. How do we do? I think we did pretty well. Math works, right? Math works. Tyler, better than 2 pokes in the eye? 2 for 2? I'm counting that. I'm counting that as a win. Okay, So what happens then when we have x's and y's in our differential equation, right? Well, now we've got a slope field that depends on both the x coordinate and the y coordinate. And so when we're matching, when my differential equation depended on y only, it was easy to see that we had the same slope, identical slopes all the way across, right, horizontally for a given y coordinate. When my differential equation depended on x only, it was easy to see that I had identical slopes all the way down vertically for a given x coordinate. Now I've got a slope field that's dependent on both x and y. So let's see how that affects our graph. So now my chart is going to have to take into account both x and y coordinates. So now I'm going to make an x, y, dy dx chart. Everybody down? Because my slopes are going to depend on both x and y. All right, there's some things that are going to be helpful, and this will definitely make your matching more efficient on Friday. For example, what I refer to affectionately as, right, key slopes. What key slopes could we use to speed up this process? Well, for what values of x and or y are my slopes 0, that is horizontal line segments? Well, whenever which coordinate is 0, do I have a horizontal slope? When y is 0, but x isn't 0, right? I've got undefined when x equals 0. So we're going to go ahead and fill in, right? Whenever y is 0, I've got a horizontal line segment, except that's the case when x equals 0 as well. So I'm going to go here. Everybody good? We got horizontals for those 6 points? Yes? What happens when x is 0 and y isn't? Then I've got a vertical line segment. So where are those? Here, 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 here. My slope is indeterminate at the point 0, 0, because I get 0 over 0, right? And remember, that doesn't equal 0, and it's not undefined. We can't tell what that is just by looking at it, so we're going to leave that. What about some other points? Well, now let's go ahead and choose. So what about 1, 1, negative 1, 1, negative 1, negative 1. We're going to have to make more. 1, 1 gives us 1, negative 1, 1. So at 1, 1, here we are. We need a positive 1 slope. Yes? At negative 1, 1, we need a negative 1 slope. At 1, negative 1, we would need a negative 1 slope. At negative 1, we have a positive 1. Okay, well that's good. What else? So we gotta get some more. So you guys want to do 2, 1, 1, 2, and then we'll grab the negatives while we're at it. So 2, 1 makes a 1/2. 1, 2 makes a 2. And you can start to get an idea for the slope field. So at 2, 1, we are at a 1/2. At 1, 2, however, we're at a 2. And so it looks like we're steeper as we go higher, right? Steeper. 2, 2, 1. Negative 2, 2, negative 1. Negative 2, other one, negative 1/2. And 1/3. Now we go. You guys see? Negative 3, 3, 3, 2, 3 halves. Negative 3, 1/3. Steeper, 1.5, 1. How's that? 2/3. Yeah? As we get into complete, looks like I'm less steep. And steeper. -2 and -1. And what in the world? Okay. How are we going to draw this? I don't know. We need bigger. So we want to do 2, 1. So where's 2, 1? 2, 1 is here. And I've got leveling off here. And and then up. I don't know what that's gonna look like. I feel like we don't have big enough. Should we find a particular? Let's find a particular on C. I don't know what this looks like. Let's check it out. So, can we separate the variables to multiplication and division? Yes? Alright, so let's go ahead and separate that. Let's get all the y's on one side by dividing, and all the x's on the other by multiplying. So I get dy over y equals dx over x. And can I integrate? Yep, we'll integrate both sides. And I'll get absolute value for my inputs in each case. So ln of absolute value of y equals natural log of absolute value of x plus c. And I'm wondering if I want to solve first this time. I think I kind of want to solve first this time. Did you worry about plus minus, or did you plug it right now? You don't care? Let's solve first. Let's do e to the. So e to the ln of absolute value of x plus c. Break up. E to the c times e to the ln absolute value of x. And we'll let the bars be plus or minus. And what's e to the ln of absolute value of x? X, right? E undoes the natural log, so e to the ln of blah is just the blah. Our plus or minus e to the c is a constant. We'll call that a. And now when I plug in the 2, 1, I see that x is 2, and the absolute value of 2 is 2. And y is 1, and so a must be 1/2. Are you guys getting 1/2? Yes? Awesome. So I probably should show that. So 1 equals a times 2. So a equals 1/2. Alright, I'm dying to see what this looks like, because I couldn't tell with my slope field. So we'll go back to here, which means y equals 1/2 absolute value of x. Let's see. I'm a little skeptical. So how is that going to fit that? I don't know. We said 1/2 absolute value of x. Oh. Is what's the value? What's the value of my derivative at x equals 0, y equals 0? At that point that we didn't know. All right, what's the value of this, of the derivative of this function at 0, 0 at the origin? It's not 0. What's my function? What's my function, junction? Y equals 1/2 absolute value of x, right? What feature occurs at the origin 0, 0? A corner, right? A corner. What's the value of the derivative dy dx at a corner? Does not exist. It's undefined, and we couldn't put anything there. We didn't know what to put there, right? Well, it turns out there's a corner, an abrupt change in direction on my solution curve at the origin 0, 0, so we couldn't fill in the slope when we were looking at it, and that's why we left it blank. That's pretty sweet. So yes. So we've got our solution curve that we saw only algebraically, right? That's pretty sweet. Whoa. Whoa. That works. That's awesome. I didn't know. I made that up yesterday. I didn't know what that was going to look like. So that's pretty cool. All right. So you guys, this is taken from an actual AP question. I just rewrote the directions because it was small. This is from an AP question. In fact, you might recognize it from some of our prep last year when we did our practice exam right before the test, the one that counted for a grade. So go ahead and do this one with your partner and check.
That's very cool.
Okay, ladies and gentlemen, so this was taken directly off of an AP question, these indicated points, and I went ahead and just used the little line tool, and so I did it quickly yesterday after school, but I was hoping we had something like this, so raise your hand if you had something like this, a little steeper there. Yes, awesome, way to go, you guys. Our final thing is going to be a prelude, if you will, to Friday's skinny day matching activity. So how can we match a differential equation with its slope field? Well, we've got some things that'll help to make it more efficient. So we can consider, right, if the slopes are all the same for a particular x coordinate or a particular y coordinate, that's an indication that we just depend on either x or y, right? We can also consider key slopes like when, right, for what values of x or y would my slopes be horizontal, zero slopes, versus for what values of x and or y would my slopes be vertical tangents, undefined, right? That can help narrow down the choices. And finally, for what values of x and y in general are my slopes positive versus negative? So just so that we have this on our notes, I want to go ahead and consider key slopes. So our key slopes to consider to make the matching process more efficient. We want to consider for what values of x and y are my slopes positive versus negative or 0 or undefined. That is vertical tangents. By considering for what values of x and y my slopes would be 0, undefined, positive versus negative, I can make the matching process more efficient. All right, so as we consider our slope fields, well, right away I see one. I see that first one has identical slopes, right, all the way across the given y coordinate. That's an indication that it must be given by which differential equation? Who's got that first graph? Riley? B. Yeah, it's got to be B because that differential equation, right, the slopes depend only on the y coordinate. So they're identical for a given y coordinate horizontally across. So our first one here must be B. Awesome. All right, so let's use our key slopes now to narrow down our remaining choices for A and C. What values of x and y result in a horizontal slope? So it looks to me like I got a horizontal slope here right along y equals x identity function. And so in order to have a horizontal slope like 2, 2, would C produce a 0 value? 2, 2? No, 2, 2 would give me 4, would give me a steep slope. So 2, 2 would be a steep slope. And here I got a horizontal slope. So when x and y are the same, that's how I get 0 slopes, and that's why my identity function line. So this must be A for the last one? Yeah, A? Huh. Yeah. Which means that, let's just check it though, opposite values of x and y would result in horizontal slopes. So -3, +3, those are opposite values. That would result in, oh, right here, C. So I'm getting C for the middle one. So BCA? BCA? Awesome. You guys are going to get a nice chunk, and I'm going to be able to check out, right? Check out your Unit 4 test. First, let's go ahead and just think. No, about our lesson today. Given a differential equation, how does one construct a slope field? Yeah, that was me after school. I wrote these this morning at 3:45 in the morning. I printed this out after school when I didn't have it yet, so I wanted you to have a template, a place to write it. Cell phone. What's the difference between a general solution to a differential equation and a particular solution? And lastly, when matching a differential equation to its slope field graph, what key slopes can be considered to make the process more efficient? Please be ready to share. Okay, ladies and gentlemen, just go ahead and share verbally, in general, how do we construct a slope field when we're given a differential equation? So what is it you do procedurally, right? What do you do procedurally? Kobe?
So at each point you convert the y coordinates to draw a little line of the slope that you do that.
Absolutely, right? You can calculate the slope based on the differential equation. So I'll typically make a table of values and sketch a mini line segment, right, to represent the value of the slope. Make a table of values using dy dx, and then draw mini line segments to represent the slope at each point. Two, what's the difference between a general solution to a differential equation and the particular solution? Vivian?
Does a general solution include like the plus c, and then particular solution uses a point?
Absolutely. The general solution is the family of solution curves with that constant of integration, right? We don't know, we don't have it pinned down, it's the family of solution curves. The particular solution is the single solution curve that contains that given condition or initial value or that given point. Absolutely. So the general solution is the family of solution curves. It's the family of solution curves of all potential solution curves, and it includes the family of potential solution curves, and it contains the plus c. And the particular contains the given point. Satisfies the given condition. Awesome one to go when matching a differential equation to its slope field graph, right? What key slopes can make the process more efficient? So what kinds of things would you like to consider, right, to help with that? Tyler?
Values that are 0.
Yeah, so what coordinates x comma y result in slopes that are 0? So we have horizontal tangents, undefined, and I'm going to keep going with the party positive versus negative. It's helpful to me too. Awesome. The last thing that I didn't say right there is if slopes are identical all the way across horizontally or identical all the way up and down vertically, you can pin down whether it just depends on x or y. Good job today, you guys. So the rest of the time you'll have to work on OTL. I'll go ahead and stop the recording and save it.